You're listening to the Thesis Review podcast. I'm your host, Sean Wellick. I'm a PhD student at New York University, and my research focuses on machine learning, natural language processing, and structured prediction. On the Thesis Review, I'll interview researchers from around the field, centering the conversation around their PhD thesis. In addition to exploring the technical content, this will give insight into their history as a researcher, allow us to revisit older ideas, and provide a valuable perspective on how their research and the field itself has evolved since their PhD days. My guest today is Ken Stanley, who is currently a researcher at OpenAI, where he leads a team on open-endedness. Previously, he was a professor of computer science at the University of Central Florida, co-founder of Geometric Intelligence, and head of core AI research at Uber AI Labs. His research focuses on neuroevolution, evolutionary computation, and open-ended evolution. His PhD thesis is titled Efficient Evolution of Neural Networks Through Complexification, which he completed in 2004 at the University of Texas. We talk about evolving increasingly complex structures and how this led to the NEAT algorithm that he developed during his PhD. We discuss his research directions related to open-endedness, how the field has changed over time, and how he currently views algorithms that were developed over a decade ago. The Thesis Review is available on SoundCloud, Apple Podcasts, Google Podcasts, and Spotify. And be sure to follow us on Twitter at Thesis Review. If you'd like to support the podcast, you can contribute $1 at buymeacoffee.com/thesisreview. There are links to Ken's thesis and the papers that we mentioned in the show notes. And now, here's Ken Stanley with Efficient Evolution of Neural Networks Through Complexification on the Thesis Review. Your thesis deals with evolutionary methods, and kind of if we could start at the highest level, we could think about some kind of trade-off between trying to design parts of intelligence or design a process that yields intelligence. So do you think that one of these is harder than or easier than the other?
Yeah, that is a good question. I guess I come in strongly on the side of designing a process that itself generates intelligence. And that probably explains why I started out with the angle that I did with like neuroevolution, because I guess I figured like, okay, we want to design something like a brain, and I like neural networks, so I kind of believe in their long-term capacity to produce something pretty powerful. But I certainly don't know what to do to put the neurons together into something that's like a human brain. I mean, I certainly have no idea how to do that. And I think that is probably an extremely complex problem to assemble by hand, a brain, whatever that means. And so it seems to me, though, that when we look at nature and we see where brains come from, that they come from a process which is actually easier to understand than the brain itself, which is evolution. And I get my intuition is that evolution is much easier than building a brain to understand. That's not to say it's easy, though. I think that like natural evolution is actually very misunderstood and maybe not fully understood even still. But nevertheless, it's probably more understood than a brain. And so if we could create processes like evolution that have the capacity themselves to build brains, that's probably easier than building the brain ourselves.
Yeah, that's a good point, that we might actually understand the process itself more than, for example, the brain.
Yeah, that's my instinct. Yeah.
Maybe let's go back to before the PhD. Did you have, like, what was your background before you started the PhD? Did you know that you wanted to kind of focus on these types of questions?
Yeah, before the PhD, so I went straight from college to PhD, and I was at University of Pennsylvania for college. And I knew I was interested in AI. At least I knew that. I was interested in AI since probably I was like 8 years old, about. But I think my earlier interest was in like conversational systems, probably is what you might call it. Like I wanted to program the computer to have a conversation with me, starting at the age of
Mhm.
8. And I was trying to do that like in the basic programming language because my Commodore 64 had BASIC. So I was making little chatbots and things like that. And
Mm.
I actually thought at the age of 8 that like if I could just get the right book, like it would just tell me how to make like a human level bot, I thought it must be like there's just some formula you need or some program that I needed to know that I just didn't know. I didn't realize it was like one of the hugest problems like that exists. But by the time I got to college, I had realized that this is actually a really hard problem. But I was focusing on natural language, I guess, at UPenn, just because I came out of that like thinking about talking to my computer mode of thinking. But I was also really interested in surprises. That was another thing I wanted. The thing that was frustrating me about making chatbots was that I knew what they were going to say. And I wanted them to say things that would surprise me and that I didn't expect. And so I think that sort of leads to my eventual interest in open-endedness, like systems that produce things that you can't really predict. Um, and so by the time I got to college, I was kind of in that mode of thinking about natural language and surprises, I guess. But then I saw neuroevolution quickly after I joined grad school, like evolving neural networks, um,
Hmm.
thanks to my advisor, Risto Mikalainen. And that was just like totally caught my interest. I was like love at first sight. I mean, I was super fascinated by the idea of evolving a brain suddenly.
Hmm.
So my interest switched, I guess, when I started grad school.
I guess you alluded to it. Did this idea of evolving a neural network, did that idea exist?
Yeah, it did exist, and even the word neuroevolution existed, although all of it was pretty obscure from the perspective of mainstream AI. But there were people doing that, and I was very strongly following that literature and trying to read all of it. And I knew like the main papers in that area. So I was a pretty strong follower of neuroevolution, but it was so different because it was so obscure at the time. So it was very different than it is now. But I guess I was like in 1999, at the end of 1999, which was like one of my semesters of grad school. I've read like every neuroevolution paper I could find, and I kind of had the belief that I was like just gonna finally figure out what all the good ideas are here, because I really wanted to figure out how do you evolve a brain like a human brain. And for some reason, I was very focused and obsessed on this question of evolving like a human brain. And so I just read everything I could, and I was taking notes and trying to like I thought maybe I envisioned that I would just take all the best ideas, combine them together, and it would be like the ultimate neuroevolution system or something like that. So certainly there was stuff preceding me, but it just none of it was really very well known.
Yeah, that was one thing I was wondering about as I was reading through, especially like the introduction. There's a lot of background in term like coming from the biology side. So was it kind of your interest in this problem that like drove you to learn more about that, or did you actually have a background in kind of the evolutionary biology?
It was it no, the interest in biology came with the interest in neuroevolution, I guess. So I didn't start out like as an evolutionary biologist or knowing a lot about it. Um, other side from just regular like high school education. But I yeah, I started to feel like I needed to understand what actually happened in biology that can explain how brains could evolve. Because I thought it was just absolutely the most fascinating question, like this unguided process, which is evolution. Like it's not an engineer, it's not sitting down and trying to figure out how to build a human brain. Like yet it did do this, and it created this thing which is like astronomically complex. And over decades of trying, no one has been able to come close to reproducing. And I was just like, how did this happen? And there's like two ways to go at the answer. One is like algorithmically, like through AI, and just like say, well, let's build something like this and see if we can reproduce this kind of phenomenon. And the other way is to try to understand from the biological side, and hopefully they converge together. So I did start to take in grad school. I took some evolutionary biology type of classes and got into that at the same time, and also neuroscience, like at the same time as I was doing like the machine learning stuff.
So the title of your thesis is Efficient Evolution of Neural Networks Through Complexification. So hopefully we can flesh that out a bit. And I think at the center of your thesis is this technique you developed called NEAT. So did you want to just introduce like what does NEAT stand for and what is the goal of NEAT?
Yeah, so NEAT stands for Neuroevolution of Augmenting Topologies, and that means like evolving brains that get bigger over evolutionary time, basically is what it means if you put it into regular English.
Hmm.
And so what it represents is, I think, a shift in thinking away from optimization, which is sort of where I think neuroevolution was largely focused at the time I appeared. As in, like, people were thinking, okay, here's a neural network, let's optimize the weights to solve a problem. And I was thinking, this isn't really the interesting question, at least when it comes to evolving a neural network. It may be interesting in terms of solving a problem. Maybe it's one method that's on the table that could be useful, but I'm not really interested in solving a problem. Like, what I want to understand is, how do astronomically complex things come into existence? Like, that was really my interest. So I saw the interesting question is, like, how can we describe an algorithm that can basically increase in complexity unboundedly forever? So that eventually maybe it will actually describe something astronomically complex, like a human brain. And then I could understand, at least, maybe it wouldn't be a human level brain, but at least I could understand how something like that could come into existence. So NEAT is an attempt to be this kind of algorithm that basically performs what I was calling complexification, or increasing complexity over generations. And and so it's kind of centered around this increasing complexity theme.
Yeah. Yeah, that's interesting because my question was going to be what is the kind of motivation for um, evolving both so neuroevolution, I guess, to take a step back, is evolving or finding both the sort of architecture of the network as well as the weights. So what is the motivation for doing that versus just having a really large network and just finding the weights? But
Mm.
it seems like, based on what you said, that's not even the right question. Like the really interesting part that you were going after was, how do you build something that gets increasingly complex?
Yeah, that's true. Yeah, and these motivational issues are so important, but they're so elusive, and I mean, they get forgotten. When you think about why are you doing something, or why is something important to do, it's true that people often will think in the framework of their own work. So it's like, yeah, you may be working on, I have a big network and I'm trying to optimize the weights, and then you see something like NEAT, and you're like, but yeah, why do that? Like, we just start with a big network and we'll optimize the weights. But it's true. Actually, I'm actually looking at a kind of a different question. And it's not just from the deep learning side that this problem comes. I think it comes from the evolution side too. Like the evolutionary computation community um, was also kind of optimization focused at that time. And so, like that's like, to me, so that's sort of saying, well, how can like selection, or like evolutionary selection, be used as kind of an optimization algorithm? Is a different question and motivation from what I'm actually or was interested in at that time, and that was more like the issue of, like, what is it really that's amazing about evolution? That was sort of more my question. Like, it's not. I don't think that optimization is what's amazing about evolution. Like, it's more of this kind of complexification aspect that's really fascinating, because, like, from an optimization perspective, it's true that, like, you can look at something like gradient descent, and it's hard to figure out, like, what exactly does evolution offer that is better if you have a gradient, like in a very high dimensional space. But evolution is still about something bigger than that, I think. It's about building structures of astronomical complexity and how that happens through unguided processes, and really understanding algorithmically, like, what something like that looks like. And it's true that, like, the thing that you get at the end of that, maybe you could optimize part of it with gradient descent, or I don't know, but it could be that it has its own internal optimization algorithm that it evolved. But it would be answering a different question, and it's about sort of a different topic.
So then, how did this compare with the methods at the time? Then I guess they just didn't do like this complexification.
Well, so there were kind of two classes of methods at the time. There was what I was calling, like, fixed topology neuroevolution methods. And those, like, yeah, you would just say, here's the structure of the neural network. Let's just evolve the weights, which is very simple. You can use simple evolutionary algorithms to do that. You can obviously not use evolution and just use backpropagation. And then there was what I call topology and weight evolving artificial neural networks, or neuroevolution. And that would be like, they could evolve the actual topology or the architecture. And of course, I was more interested in the latter of these topology evolving things, because it relates to complexity, but almost none of them were really about increasing complexity. They were more of an optimization viewpoint, even though they could evolve topology. Like they were kind of come from the perspective that there's a space of topologies, like, but it's not like unbounded. Like say you think of it as a bounded space, like within up to 100 connections or something, there's lots of topologies you could have. Let's find the best one. And that's like the optimal topology for this problem or something like that. And that is like, again, very different, I think, from where I'm coming from, because I'm thinking of unbounded and like, I don't know how big the thing is that I need. And I want to be able to just get bigger and bigger and bigger. And so I think it's still philosophically different, except there are some exceptions. There's something called the Saga algorithm from Harvey, which would increase the size of neural networks every generation, but all the neural networks in the population at the same time. And that's probably the closest precedent to NEAT, because it was strictly going to it was increasing complexity, but it was very preliminary in the sense like everything would increase in complexity in the exact same way, all in lockstep at the same time. So in some way, it's not really natural, and it's sort of an all of your eggs in one basket approach, which it doesn't look like nature to me, where nature's got all these different designs all at the same time being evaluated and all going in divergent directions through the search space.
Hmm.
So I'd say there wasn't really anything like neat at the time. And in fact, and this is like at the end of 1999, when I kind of sat down and said, okay, what have I learned? Because I spent this whole year like reading all of these references. Um, I didn't have the feeling that I expected to. What I thought was I would have all of these good ideas and I would collect them, and combine the best ones. But instead, I had this real kind of empty feeling. And I don't mean to say anything derogatory about the field. I mean, the field is where the field is at, because I mean, these are people who are pioneers who were doing things for the first time. But I think it
Hmm.
was in a very early stage, and I kind of discovered that like no one really had cracked this problem. In fact, there were several known outstanding challenges that were just not yet understood. Um, and I um, and I was just like, something completely different is necessary here. Like this is like I'm not going to be able to just combine some ideas. Like I just need to start totally from scratch, thinking about this problem. So, which is why Neat event ultimately is very different. Um, it's not really like any other algorithms that preceded it.
As you were developing it, though, like I guess there is this high level goal of getting increasingly complex, like arbitrarily complex. But I guess ultimately you have to work on some kind of waypoint. You have to like pick a task. So how did you? I think here like the first task you do is this pole balancing.
Yeah.
Yeah, how did you like pick a task versus balancing it against like this higher level motivation?
Yeah, so the task came secondary to the algorithm. The task just happened to be the benchmark of the time, and it like at that time in RL, like pole balancing was a big deal. It sounds ridiculous now,
Mhm.
but back then it was really like the record holding algorithm in pole balancing was a neuroevolution algorithm, like that already existed actually. And there were also RL algorithms that were trying pole balancing. There were different types of pole balancing. There was like double pole balancing, which is harder than single pole balancing. Like, it was a whole thing. It was like
Mhm.
the Atari of its day or something. And I kind of got sucked into that. I feel like, because I feel like it really doesn't represent my interests very well. But it was an accident that Neat got the record. Like that's why I got sucked into it. Like I just tried it on pole balancing right after I got it working. I finally tried it on pole balancing, and I was in shock, absolute shock, that I was like the best score like ever recorded. Like that was not what I was expecting, because I wasn't really interested in things like pole balancing. Um, but then once you beat the world benchmark, you're like you can't just like forget about that. So I mean, I was like, is this for real? Like, it actually is the best score ever. And I like tried it again, and it's still like amazing. And so I kind of got pulled into pole balancing, but I think like the algorithm design phase where I was like coming up with algorithm, I wasn't even thinking about pole balancing at all. Um,
Yeah, yeah.
yeah, it was more what I was really thinking about with Neat when I started to like I sat down. It was like early January of 2000. Somehow that seems strange to me because it's like right at the beginning of the century, and I was in my parents' kitchen, and I just said, okay, I have to do this now. Like I've read all of the literature there is to read, and now I have to figure out what to do. And I was the first thing I was worried about was how do you combine networks that are different topologies. And this is a known problem. in the field, or it was, and it was called the competing conventions problem sometimes. It's like if you have two different ways of doing the same thing and you're going to cross them over, which is an evolutionary thing like mating, it doesn't really make sense. Like it's hard to know how to combine arbitrary topologies. So I was like just making scribbles and stuff, trying to figure out like, is there some other way of solving this problem? And it was in the process of doing that, like basically at my parents' kitchen, that I stumbled onto something called historical markings. Eventually, I called it historical markings, which basically really addressed the problem well. Like it was a great solution. I don't know if its solution might not be exact right. It's like it addressed the problem. It allowed you to get around that problem, and and so that was like it happened in a matter of like a minute. And I even put the scribbles like from the notebook where I was drawing these diagrams to figure this out. I put them online, so they're all available historically. Like you can actually see me scribbling and figuring out the neat algorithm.
Maybe I'll tweet those out.
Yeah, I could give you the link, because I think I'm really interested in how people thought of things, and you never get that kind of that insight from papers. So I wanted to share it. I know most people probably don't realize it's even there, but it was an absolute like eureka type of. I mean, people say that doesn't happen in science anymore. That's why I want to mention that. Like for people who are like PhD students or college students listening, like that can happen. I just like was like, oh my god, I just figured something out, like amazing. Like this was so neat. Like yeah, to overload that term. And I was just I was like immediately knew that this is like it's very significant. And it wasn't like I spent months and months. It was just like a matter of minutes. Um, and it was so I figured out this historical marking thing, and then the rest of the algorithm very quickly flowed out of that. Like once I knew how to do that, I realized you could do speciation, which turned out to be very important, maybe more important. But if you know, historical markings allows you to know what lines up with what if you're comparing two genomes or two networks, for example. And so that helps you to cross them over. But if you can do that, you can also know whether they're in the same species. Like if I know like the relationship of one topology to another, I can tell how close they are in some sense, distance sense, and then I can group them together or cluster them by their similarity. And it turned out that this idea of speciating was very, very helpful for like preserving new ideas, protecting new ideas, and things like that. And so that I immediately saw that's probably really good for this algorithm. And then complexification was like the third element of it. Like once you have this protection in place, then you can do complexification. It turns out, like if you don't have this protection of speciation, then increasing complexity doesn't work very well. Because the thing is, when you increase complexity and you increase dimensionality, it gets harder to optimize something. And so if you have bigger things competing with smaller things and the bigger things take longer, then the bigger things are going to die out and the smaller things will take over. And you can never really bootstrap up to higher complexity. But once you have speciation, suddenly you can protect the bigger things because species sort of provide a form of protection. And then you can actually bootstrap up. It's like you have a new idea, you protect it, and so it has time for it to actually realize its potential. Just like grad school, kind of like if you're a new student, they don't just kick you out with the first idea that doesn't work. And so this principle sort of showed itself inside of NEAT, and all these things tied together really well. And there, the NEAT algorithm just popped out January 2000 in my head, and I spent the next 6 months trying to actually like write the algorithm, which was its own kind of odyssey.
Those were kind of the three principles that you highlighted in the thesis. So the historical markings, the innovation through the speciation, and then the complexification. I really liked this innovation. Yeah, it seemed like it had this kind of philosophical connotation to it that like you could even think of like the field of research itself as having this problem that
Mm-hmm.
we might have like very state-of-the-art methods and we might pass up some more promising methods that aren't as strong currently but might be strong if we just let them kind of develop further.
Yeah, yeah, absolutely. And I think like it seems almost like in the field of AI that if you really do have a useful insight, it should be about more than just an algorithm in some sense, because like intelligence is sort of the thing that holds together everything that we do. And so we should be gaining insight into ourselves in some sense, I think, if we actually have algorithmic insights about it. And so this kind of phenomenon of like, okay, here's an algorithmic idea like the speciation and NEAT, but there's a higher level philosophical interpretation which applies to like the way you run innovative systems or society or things like this or
Hmm.
research. I think it's the way that you kind of things you would expect to go, or you would hope. It's almost a validation, and I think it's an important aspect of validation outside of just results. You know, like should you be more interested in it because it did really well in pole balancing, or because it actually resonates with something that you understand about the way that the world works? And I think both sides of it matter. You know, I'd go with more with the latter. I care less about pole balancing. But this idea that like I suddenly understand something a little better about why it's important to do things in a certain way in this world, makes me feel like the algorithm is getting at something deeper, about innovation and intelligence.
And yeah, so I guess maybe for those who haven't read the thesis yet, hopefully they will after this podcast. I guess like to kind of summarize it, you're building this network topology with a series of or these genomes that encode different structures, and then they'll have mutations as well as crossover, and over time the structure will kind of grow by adding nodes. Is that a good summary?
Yeah, yeah, that's a good summary. And I mean, what makes it work are these other ideas like historical marking or speciation. Like if you just do that, what you said, like if you just create an algorithm that just adds structure over time through mutation, it's very simple and very easy to understand, but it won't work very well. So it's like to get it to work, you need these other kind of elaborations of the algorithm, which I think are the more like the important insights of NEAT that it adds to the field is to actually get something like that to work and happen the way you would hope it would happen. And then you really get increasing complexity that actually gets better over time and more complex over time.
Yeah, one thing I wanted to ask about is to kind of jump back between when you're developing Neat and then the present time. So,
Mm.
like at the time, did you ever envision that we would be using networks that have, millions and billions of parameters? And do you think that that might require a separate approach, like not completely building from scratch?
Yeah, that is a great question for to think about in hindsight, because there's some important insights there. I think that yeah, things have moved way beyond where they were 20 years when I had this idea, um,
Hmm.
and and so it it looks like yeah, it's true that I don't know if I envisioned that the world would be like this today. Like I did at some point start to think about networks with millions of connections, and also realize that Neat wouldn't give you them. I did realize that. I don't think I knew that they would be being optimized with gradient descent or something like that 20 years later. I didn't know that, or billions or soon trillions of connections.
Hmm.
But so so then that makes me now. So what do I think now? Now I think so. It's the question it raises now is like, what is it? What is the significance of what NEAT showed? Because one originally NEAT was supposed to be like a way that you could get up to high complexity. So now you could say, well, now
Right.
today we see that you can have really high complexity, optimize things of extremely high complexity. You don't need to complexify up to it. It just optimizes directly. And I think I have to concede that I'm a little surprised, or I was a little surprised that this actually works, because I thought it was something that NEAT showed is that like it's really hard to get into high dimensional space if you don't ascend up into it from simple to complex. Like that was kind of
Mm.
an aspect of the theory behind NEAT. And so it turns out that actually you can optimize very large complex structures as long as you have some kind of supervisory signal. Um, but actually, if I think back now, like it doesn't mean that the complexification principle is somehow diminished, because like if you think about it, it wasn't about how to send a gradient back through a giant network with a lot of connections and optimize ways.
Hmm.
It was about more this something that's more related to evolution, I think, which is not being optimized through gradient descent. Like there is a puzzle here about like how did evolution create these astronomically complex things without gradient descent? Like when people compare evolutionary algorithms to gradient descent today, I mean, a lot of people think that the gradient descent like crushes evolution. Like, why use this kind of like very blunt instrument when we have this very specific way of doing things now that makes more
Hmm.
sense? But you have to think that. But you have to think and look at evolution. Don't forget that actually it did create these things without gradient descent. And I still
Mhm.
think that we need to understand how that happened, because that is an incredibly powerful process, and it remains more powerful than anything gradient descent has done so far. Because after all, it created us and our brains, which are arguably more powerful than anything that exists right now in artificial intelligence by far. And yes, we may catch up, but we haven't yet. And so it still behooves us, I believe, to understand how it is that something like that could work. And NEAT remains, I think, very useful in thinking about how systems like that are possible, because it shows how complexification can move up into higher dimensional spaces effectively, and that actually there's different properties in a search like that than there are in a gradient descent driven search. Like if you look at the
Mhm.
structural properties of neural networks that have been evolved through neuroevolution, through complexification, versus the properties of these giant spaghetti things that have been evolved, that have been optimized through gradient descent, you will find very significant differences. And we could go into those kinds of things. And those
Mhm.
reflect the different types of optimization process, or even search processes, I might call it. Because I guess even in neuroevolution, I've moved away from thinking of it as optimization over time. But search processes have very different properties in the kinds of things that they create. And in some ways, the neuroevolutionary form of search is like a lost art form. Like it has
Mhm.
insights to give us, and it can do things that gradient descent doesn't do. But it is being overshadowed now and crowded out by the amazing, spectacular results that we're getting from gradient descent. So it's like the stained glass window or something of deep learning. We've kind of forgotten how to do the art, but I think we shouldn't forget this art, because it does have some really interesting lessons still that remain.
Mhm. Yeah, one maybe this touches on what you said. Like one interesting thing that I found going back and reading this is like the generality of the search that Neat is doing versus like if you look at some for example, like some of the neural architecture search papers, I'm not familiar with all of them, but I know like some of them will basically specify like different layers to
Hmm.
search over. And that's already like prescribing the idea that our network should be made of these different layers and it's just a matter of like how to put the Lego blocks together. Whereas like in here, I think you had this application actually to Go that you worked on. And
Oh
it
yeah.
was really interesting that the network was actually, since it can just evolve arbitrary recurrent connections,
Hmm.
I think it actually like learns some notion of memory over a few time steps, which is something that you'll never get by just stacking layers together. You need like something more general,
Yeah.
if that makes sense.
Yeah, that's true. That is true. And like that, I guess that's so that gives a nod to architecture search, which is a topic that people today are interested in deep learning. So it's moved ahead in a lot of different ways now. But some of them still even use neat inside. Like there's code deep neat, which came out of sentient recently, and now they're part of cognizant. But so you still see neat like principles coming up in architecture search type of discussions. But I think there's actually um, well, that is interesting. Like in sort of like a arbitrary recurrent structures and things like that, you can find with algorithms like this that are potentially hard through other means. But there's actually something else about it. I think that's unique in that when you start to combine neat with what I would call like non-objective searches, like searches that are not trying to actually solve a particular problem. And
Mm.
I would put evolution in nature in that category. Like if you're trying to evolve, like if you're thinking about evolution, it doesn't have a single target organism that's trying to create. It just actually creates all of living nature, which is one of the amazing things.
Hmm.
That's what the sense is, which it's open-ended. And if you look at processes like this, and novelty search was an algorithm that we developed years after NEAT that is a bit like this, that it's basically just searching for novelty, not searching for an answer to some problem. Then
Hmm.
I think what you see is that you can see phenomena with an algorithm like NEAT that you wouldn't see or can't see with deep learning. Like that you see things like that if you do something in a non-objective way, like a novelty search, and if it solves a problem doing it non-objectively, in other words, it's not trying to solve the problem, but it solves it as a side effect of doing something else like searching for novelty, then what you find is that you get much, much more compact solutions than if you try to solve it by actually trying to solve it, which sounds like very paradoxical. Um, but there's important lessons in there that like the way that what happens to structures when you actually trying to solve a problem explicitly is that you tend to create spaghetti, because like any tweak that you make that gets you a little bit closer, like makes that reduces the error a little bit from where it was, that will be locked in. So you get lock in after lock in after lock in, which basically gives you this total spaghetti thing. But if you're searching for something more like novelty, then what you get is like that each increment in discovery is like a whole new thing. Like you find something like symmetry. That's like something new. And so you're not locking in these tiny little spaghetti type of changes. You're locking in overarching types of like general principles as you move forward. And if you create a succession of general principles that have been concatenated with each other over time, you get a way more efficient structure and representation. This is widely not known in deep learning. Like nobody talks about this right now because it's obscure from the perspective of like gradient descent. But you can't really see it with gradient descent because there is no structure to that you get. Like you just get the topology is always the same. But like with something like NEAT, you'll see that like if you do a novelty like search, then you get these very compact, amazing representations. But if you do like an objective driven search, they're like triple the size, like every time. And so we learned something about like the nature of representation, how it relates to how you conduct your search, that you basically can't learn without these types of searches, like something that does complexification. And it raises questions about like what type of search is appropriate for what. Like evolution is used to describe the brain. It's not used to describe the things that the brain learns. The brain eventually learns some things like over your lifetime, but the brain itself is being described by a process that's much more like a non-objective complexifying process than it is like a gradient descent through weight space. How important is this to be able to ultimately describe structures of this type? It seems like if you wanted to get to a structure of this type through an objective driven process that wasn't complexifying, you're going to get a very spaghetti representation, and that could be a problem because bad representations means that it's harder to search for new stuff from there. And so I think basically there's still a lot of subtle, interesting things, but they've become more subtle. Like 20 years ago, this would be like radically interesting, and just complexification on its own. It's like obviously amazing. We're just gonna get more and more complex. What's gonna happen? I was excited about that myself. I was like the first time I ran NEAT, what is gonna happen? But now that's kind of less exciting because you can just optimize multi-billion dimension structures with gradient descent, and like, well, why do we need complexification? But these subtle issues still remain, I think, and is why like these issues or this kind of algorithm I think should still at least be on the map.
Yeah, that's a good lead-in then to this idea of open-endedness that you mentioned. So this is kind of another thread of research that you've worked on throughout your career, and you have this book, Why Greatness Cannot Be Planned. And then now from what I understand, you're leading a team at OpenAI on open-endedness.
Yeah.
So yeah, could you just introduce this idea, and then does this connect with things that you did during your PhD, or is this a new thread that you developed later?
Right. Yeah. So just to start with, well, what is open-endedness? Open-endedness refers to processes that continue to generate interesting new stuff forever, basically infinitely creative processes. And the examples of those include things like natural evolution, which is something that's been going for more than 1 billion years and has invented, so to speak, all of living nature, all of life on Earth, every single organism you see in a single run. It's basically the most prolifically creative process I think that has ever existed in the universe, as far as we know. And so it's very interesting, and one of the most interesting aspects of it is that it doesn't end. That it's been going this long. Like there is no algorithm that's worth running for 1 billion years. I would assert, I believe, I often say this, that nobody can point to one right now where it would be worth coming back to see. Even if you had enough space and time, it just wouldn't be worth it. And that's interesting because this has that property. Now, I mean, I just have to acknowledge that, like, I don't know it'll really last forever. I mean, obviously, there's going to be like some heat death to the universe or something eventually. But that's okay. I mean, I think 1 billion years is close enough to forever for us to be really interested and intrigued by something like that. And it's not the only example. There's other examples like the history of human invention. You know, starting from I don't know where it starts, like a wheel or a fire or something, and now we have things like computers and airplanes and space shuttles. And the process that led to that is also in some sense one single algorithmic process. It's true it's gone through many brains, and it's true it's piggybacking on human intelligence, so in some sense it's a little bit more of a cheat than natural evolution, which didn't have that advantage. But nevertheless, it tells us that intrinsically in us, humans, open-endedness is part of who we are. Because we are contributing through the history of civilization and invention and culture and art and music and everything that we've done, science, that we are ourselves implementing an open-ended process through our brains. And so that's pretty amazing too. And so the open-endedness problem is to be able to create never-ending algorithms that have that property, like things that you start the algorithm and you come back in a week and you're like, wow, that's interesting. And then you come back in another week and you're like, that's even more interesting. And then you can come back in a year and it's like, wow, this is amazing. And 10 years and a billion years and so forth. And so we don't know how to make algorithms like this at this time, um, but we're getting there. We're making progress, and I think it's ultimately is eventually really strongly intersects with the field of AI because of the fact that our brains are the product of an open-ended process, and arguably the only way to get things like us is through an open-ended process. And this is not often discussed in the mainstream, like that, like you need an open-ended process to get like a full brain-like structure. But it's interesting to put that on the table, I mean, and discuss it, I think. Because if it's true, then we really need to crack open-endedness and sort of understand what it means to create an open-ended process. And it also is important to understand the nature of ourselves. So to connect that to, was I interested in that from NEAT in the beginning? I don't think I would have used the term open-endedness. I don't know if I knew it at that point. But I think if I think about myself, I've always been interested in it. I just didn't know that. I wouldn't have been able to say it. But if you look at NEAT, it's obviously about that at some level. Like NEAT is about like that you can run this algorithm and the neural networks keep getting bigger and bigger and bigger and there's no bound. And clearly that looks like a prerequisite to something open-ended. Like we don't know when it should stop or what complexity level it should stop. And in fact, we don't even want it to ever stop. Well, you need something that keeps complexifying if you're going to do something like that. And like I think it was just like a more primitive view of open-endedness at the time. Like NEAT doesn't solve the open-endedness problem, but it looks like me trying to start to grapple with it is how I would interpret it now. So I actually think I've always been interested in it. I mean, even going back to as an 8-year-old making chatbots, um, the fact I wanted them to surprise me, I think is basically an interest in open-endedness. Like I wanted it to keep coming up with new stuff forever, basically that wouldn't be what it came up with before. And so I think there's just something about my personality that is like really resonates with open-endedness.
Yeah, I guess you can see kind of traces of it. Like another thing that you did in your thesis that comes to mind is you applied NEAT to video games, and I think the high level idea is like the network keeps adjusting as the video game is being played. So it's
Yeah,
kind of like something up front isn't prescribed. It kind of depends on what happens as the
yeah,
game unfolds.
yeah. That's a good point. Yeah, that is probably another reflection of this interest. And I mean, the difference there is humans are in the loop, but I've always been willing to bring humans in the loop in neural network systems. Like pick breeder is another example. And I so it's because like humans are open ended, so that's why it's kind of a cheat in a way, because we're already open ended. So if I bring them into the loop, then I sort of get it for free. But that's also a reason to do it because I not only want to solve open-endedness, but I just want to see open-ended processes unfolding. Because just watching them, even if I don't fully know algorithmically how to implement them without humans, just watching them is fascinating and you can learn. Like I learned from
Hmm.
PickBreeder and from that old system you're mentioning from my thesis, which is called Nero. I did learn things about how processes like that work by just observing the interaction of the people with the system, like really deep things. And so I think it's always worth it in the pursuit of open-endedness to observe what happens even with humans in the loop.
Another thing I wanted to ask that you mentioned is about NEAT again, and you mentioned like having just optimizing for was it novelty,
Mm,
and that causes different structures to emerge.
mm.
Do you think that if we were being really strict with this idea of open-ended, that prescribing novelty specifically is actually kind of imposing something on the search itself, if that makes sense?
Mm,
Like why
yeah,
novelty specifically?
yeah. Well, yeah, that does get into the weeds of open-endedness and really how to do it and whether what is novelty actually the ultimate answer to this. What I think is that to really what you really want in an open-ended process is something that's always looking for something interesting. And there are different ways to do that. There's not just one way to do that. And so it's like, what does it mean to formalize the concept of interestingness? Like if I have something interesting, like a neural network that's doing something interesting, for example, then what it means to look for interestingness is to follow a gradient of interestingness to the next interesting thing. And so it's not like we're going to any specific thing, because many possible things could be interesting. They're very different from each other. And I think that anything that can do that is eligible for being part of an open-ended system. Even that is not the full solution to open-endedness, but it's a part of it. But the problem is that we don't know how to formalize interestingness. I mean, the problem of interestingness is possibly, AI complete. It maybe you have to solve AGI to actually be able to say what's interesting. It's also a question of interesting to whom. I mean, who are we talking about here? Well, I guess to humans, but of course we all have different interests. But nevertheless, some notion of interesting is important here. And so I think novelty is really just a weak proxy for interestingness. Because one thing you can say about interestingness is that at least it usually has to do with novelty. It's like novelty plus plus. It's like not just novelty, but at least it should be like if it's not novel, it's probably not interesting. That much I could
Mm-hmm.
say. Now, if it is novel, it might still not be interesting, but at least it's novel. And so I think it was just an attempt to get a kind of a cheap proxy for what we really, really would like, is just to keep on finding interesting things. And so I think, though, in the larger picture, like from the point of view of the search, like it doesn't have to be novelty. It doesn't have to be any particular formalization of interestingness. It could even just be drift of some sort. Like mutational drift can get you through a lot of diverse places in a search space, as long as there's some criterion that is causing you to lock in on interesting things at some points. Like there has to be some focusing mechanism at some points. But there are many different kind of ways to evaluate steps through the search space that could be conducive to a divergent open-ended search. And so I think that actually it's somewhat forgiving, is my feeling. Like you don't have to have like the perfect answer. I don't think the holy grail of open-endedness is that we formalize interestingness perfectly. I don't think it's necessary. Because think about nature. Nature doesn't know anything about interestingness. And yet it produced all kinds of insanely interesting stuff. More interesting, arguably, than anything we've ever built. And
Yeah, yeah.
so I think the issue is not to ultimately formalize interestingness perfectly. I think that's not necessary. There's other things that are coming into play.
I see. Yeah. Yeah, and then maybe to talk about a something concrete that you've worked on since in this area, this project called Poet and Enhanced Poet kind of gets at these idea of open-endedness.
Yeah, sure. And actually, Poet, at least the Poet implementation that we've released in Enhanced Poet, it does actually have Neat inside of it. Funny enough, so it's still getting used, like 20 years later, which is hard for me to believe. Um, but so what Poet is, I mean, it's so this is now like 20 years of thinking, but that goes into that beyond Neat. But basically, the issue is I've been pursuing open-endedness kind of explicitly in the last few years with my colleagues. My colleagues who worked at me at Poet were at Uber AI Labs while I was there, and we were thinking about this issue that has come up now, that like over time we've learned a lot about like pushing search to be divergent, which is part of the problem of open-endedness. Part of the solution to open-endedness, I think, is like a lot of search processes converge, and clearly if you converge, you're not going to be open-ended, right? I mean, you may solve the hardest problem in the world, it's still not open-ended. Like if you solve like the hardest Atari game or something, like that's the end, it's all over. There's nothing that comes after. So divergence is very important, like the constantly moving away from where you've been. And so we have gotten algorithms like novelty search is one of the early ones that have divergent properties. And in fact, in RL, there are others. Like, I mean, intrinsic motivation is a kind of a divergent pressure in a sense. And we and so but we've recognized that there's another side of open-endedness, which is a big missing link in the picture, which is that it's not just a question of pushing the search divergently through the space of, say, neural networks. It's also the problem that there needs to also be new problems to solve. It's not just new solutions. Like I can create a problem space. I can give you a robot and say search divergently within the controller space of this robot, like a six-legged robot or something. So you get all these walking gates for this hexapod, but clearly you cannot have open-endedness there because there's only a hexapod, and like at some point you're just going to max out what's possible, and just find all the gates that you could have, and that's the end. And so where do new things come from? Where do new things to do, new opportunities to actually try come from in the world? And to get a process that could be worthy of like a billion years of running, you have to have new things to do. And so like Poet and algorithms like it, like the minimal criterion coevolution, which comes from some of my work at UCF, with Jonathan Brandt at UCF, these algorithms have started to kind of wade into this issue of, can we generate problems also, at the same time as we're generating solutions, and we're generating solutions divergently. And so if we're generating problems or searching through problem space at the same time, then presumably we can keep on inventing new things to do. And so Poet is like explicitly about that. Like on one side, you've got a population of problems, and so we call them environments. So they're different. In the domain we used in Poet was like a terrain that a biped robot has to walk over, a 2D robot. So terrains basically, and then the solutions are neural network controllers for the biped robot. And so Poet stands for a paired open-ended trailblazer. And so paired means for every environment there's a paired neural network that's trying to solve it. And the idea is like we keep on generating new environments, and then neural networks from old environments try to solve those new environments, and then we generate even more new environments. And there's novelty pressure on the environments, and the environments are getting more complex. And actually, that's the environments are getting more complex because of NEAT. Funny enough, it's still convenient for this purpose. You can imagine alternatives that wouldn't use NEAT, but it was very convenient. I mean, it was evolving basically a type of neural network for generating patterns of terrain called a compositional pattern producing network, that was just really well suited to that. And they starts out smooth because that's simple, and then they get more complex as the neural networks complexify. And so on the environment side, you have this divergent novelty pushing NEAT like process. So it's very kind of very smoothly following from my thesis work like years ago. And
Hmm.
then on the neural network side, you've got an RL like system process going, because each neural network is trying to solve its respective environment. And it's true that we do something called goal switching in Poet, where neural networks try to jump to new environments, change their goals, because that represents the sort of serendipitous nature of open-ended search. Like you never know what might lead to what. So it's like if this guy's walking well in an obstacle course, like he might also walk well in flat ground. Who knows? Let's bring him back and see. And so you're constantly seeing if there's goal switching might work. But internal to any given environment at any given time, there's always just like a kind of an RL like optimization process going on at the same time. And I think like that tells you that gives you a sense of where open-endedness comes meshes with deep learning, because it's kind of an outer loop inner loop type of situation. Like inner loops might look a lot like deep learning. Like this is why I think it's important to look at these things as complementary and not competitors. Like they go together really well. Like the idea of like a population diverging is not a deep learning concept. It's not really native to deep learning. It's more native to the kind of neuroevolutionary stuff that I've been doing. But like the idea of like a reinforcement learner getting better in a domain is very native to deep learning. But they both go together perfectly, because it's like the solving of the problems is one thing, that's a very deep learning kind of a thing. But the generation of the problem and the divergence through problem space, that's a more open-ended problem. And so they're really kind of complementary partners that go together. And I think so. Poet's sort of the latest attempt to kind of articulate that type of relationship.
Yeah, yeah. I found that really interesting when I saw the CPP, and which develops these or generates these increasingly harder environments. It was a nice like tying together of the two threads of research, kind of.
Yeah, yeah, it's kind of, I guess, pleasing to me to see like to still be using Neat after so many years.
Yeah, yeah,
And but it does fit well somehow with that, like the idea of increasingly complex environments just fits well with what Neat and CPPNs do. So it was natural
yeah.
for doing that experiment.
It would be interesting if I don't know if these types of problems exist, but it would be interesting if for certain environments, as the environment gets more complex, the network would also keep getting more complex. So it would be both things evolving at once. Whereas like now,
Yeah,
isn't it a fixed network and you're training its weights? But if
yeah,
somehow the structure of the network,
yeah. Great point.
yeah,
Yeah. Yeah, that also raises this question of, is there a modern day need? Like, I mean, obviously need is still here, but like it's it does it's right that like somehow like as the environment gets more complex, the networks get more complex is it's just so common sense. It sounds so right. I mean, we could imagine, because we're used to it now with deep learning, just start with like billion connection networks, and why worry about them getting more complex? But at some other level, that seems counterintuitive and weird, It's like we have these extremely simplistic problems that we try to solve with billion connection networks. Is this really a natural way to start a process like this? And does it really lead to the best ultimate results from an open-ended perspective? I'm not really sure. It's actually kind of confusing. At least I can say it's wasteful of computation because we're running billion connection networks
Yeah,
on
yeah.
very simple problems. But if you don't care about wasting computation, I'm not sure whether it still works out in the end. Maybe it does, maybe it doesn't. But it does seem at least worth entertaining the possibility that it's not actually going to work out as well in the end. And therefore, it would be nice if complexification was going hand in hand with Poet, which, as you point out, it's not because we were just running on fixed networks. We were just optimizing fixed networks in those environments. We kind of dropped neat on the reinforcement learning side. And so I think, but the problem is that now we know, like, we are going to be, if we're doing sophisticated things nowadays, we're not talking about dozens of connections or hundreds of connections. Like, that was the
Right.
order of magnitude of kind of neat evolved networks. And so like, we are probably going to need to have whatever neat like system doing a complexification that's much more than just like one connection at a time, one node at a time. So that's what I mean by the modern day need. Like, it's something that moves up much faster. Hyperneat is a little bit related to this. Like, there was this next generation neural evolution system that we later invented, um, which uses like what's called an indirect encoding, which allows like you to take a small network but generate a giant network from it. And that could be one answer here. We could complexify using something like Hyperneat, um, or um, or something like just more neat, like directly, like something that just describes large networks but takes bigger incremental steps when it complexifies. So it doesn't just
Right.
add a connection; it adds like entire structures all at once, or something like that. But yeah, that hasn't been done yet, and I think it's a cool direction that's like totally open. So someone should pick it off.
Yeah, yeah. So one thing I wanted to ask about Poet is kind of where you go next with like where you apply it. One thing we just had Julian Tegelius on the podcast, and we were talking about these procedural generated games.
Mm,
It seems like that might be a suitable type of setup, like suitable next step for Poet. Or yeah, how do you see kind of the
mm.
types of environments that it's being trained on getting more complex, if you will, over time?
Yeah, great question. Yeah, I'm hoping that like the people when they look at Poet and see what it can do will be inspired to try all kinds of environments with it. And these procedural content generation based systems seem like great candidates. I mean, I agree with Julian. It would be super fun to see more application. I know Julian did something like this already, but it would be fun to see more of this kind of a thing with Poet, and just to see more of like the more like exciting to watch kind of stuff that you would get. I mean, because like obviously in the biped and on the terrain is it's not as exciting as it could be. It's kind of a simple domain. It's got limits in terms of what can happen. So yeah, like to put this into a much more complicated domain, maybe something that's 3D and has a lot more affordances than just terrain, and then just let Poet go at it. Like, that would be exciting and interesting. And the whole point of it is you shouldn't be able to know what's going to happen. That's what's fun about it. Like, cool stuff will happen, but you don't know what it is. And so to conceive domains like that, where like there's enough degrees of freedom in the domain that like anything could happen, that's I think a great direction for just applications of Poet. And I hope people get creative and try things like that.
I don't know. This might be a bit of a stretch, but I was thinking about these recent results with the GPT-3 language model, and it seems like, very loosely speaking, that kind of follows this idea of not specifying the exact objective, in the sense that we it does have a fixed objective of maximizing the probability of these sequences, but then it was able to kind of discover some kind of meta learning behavior, at least like loosely speaking.
Yeah,
So it like learned to do something which wasn't really prescribed, at least thought to be prescribed in the learning process. So I thought that was pretty interesting to maybe connect to some of these ideas.
that is interesting. If yeah, so can we interpret GPT-3 as sort of related to the non-objective viewpoint?
I don't know. Like looking forward, it seems like if we're able to come up with kind of general enough objectives and maybe like enough compute that if we do set up, yeah, like the correct objective, that these learning systems might end up learning things that we don't expect just in order to solve the objective.
Yeah, I think that is fair. Yeah, that's a good insight actually. That I mean, it's not exactly, it's not, yeah, like you point out, like what
Yeah.
they, the way GPT-3 is trained is not though like a novelty search algorithm or something like that. And
Hmm.
it's not an intrinsic motivational reinforcement learning algorithm, but it is in some sense very generic and removed from what you actually would do with it.
Hmm.
Like as in that sense, it is philosophically aligned in some way with those types of algorithms. You run novelty search on a robot, and and eventually the robot learns to walk, but you weren't running an algorithm that was optimizing walking.
Right, right,
And
right.
you run the GPT-3 to predict the next token or something like that, but that's not the same as like coming up with new cooking recipes. And
Hmm.
so it does seem like there's some connection there to be made. That's
Yeah,
like
yeah.
this kind of oblique way of getting towards being actually more powerful in the end than trying to directly become powerful. Is maybe is showing up there. That's pretty interesting. I need to think more about that
Yeah.
actually.
Yeah, and then another thing I want to ask about is, I guess some people call it like the scaling hypothesis, or Rich Sutton had called it the bitter lesson. That kind of the methods that win out in the end are ones that you can kind of throw more compute at
Hmm.
and will scale
Mm-hmm.
larger and larger.
Hmm.
Do you think about that when you develop these methods, like Poet or?
Yeah, like what we're facing, I think, is just a theoretical question of how amazing can you be if you're small, and like we don't really know, but like if you need to be really big, like as in like have like billions or trillions of connections to do something interesting, then that's just a property of reality. Like that's not someone's fault. It's not like a political conclusion like that someone keep like we're going to commit to like training giant expensive multi-million-dollar models. It's more like that's just how reality is. And so it's just a question like if that is reality, what are we going to do? Like if the most amazing things just start falling out once you have trillions of connections, we're going to need expensive stuff like to do that. And certainly for the things that I'm interested in, it's very relevant because like I'm interested in things that get more and more interesting, or probably because of that more complex forever. And so you're going to start running up against these like very expensive types of complexity levels at some point, almost certainly, unless like there's a miracle and like all the most amazing things in the world are possible at very low complexity. But like that doesn't seem very likely. It seems like probably like the fact that we have like 100 trillion connections in our brain is probably because we need that or something
Yeah,
around
yeah.
there. I mean, maybe you can reduce it by a factor of 10, but that's still 10 trillion. So, I doubt it's like most of it you don't need. And so I guess I don't really see the way out of, I don't think it's like some kind of, like a political type of trap that's happening where like companies are taking advantage of something that's like academia can't do. It's more like, what else could happen here if this is just the way that reality works? And I think what we need to think about is really just how to make this kind of research accessible, given that this is turning out to be important. I mean, there's going to be some holdouts that disagree that it's important, and that's fine. That they can work on things that are small because they believe in it. And I also think that there are many discoveries to be made still on small things. Like there are principles that can still be uncovered when you work on small things, as I have. I mean, most of my career I was working on things much smaller than there are today, and still found some interesting things. Like so, it was obviously possible. You don't need trillions of connections to find interesting principles, but to see the most potential of those principles be realized, that may require really big things eventually. And so then it's a question of accessibility, I think. Like, how do we get like the average researcher access to the computation if it's necessary, so that they aren't locked out of this just big um, adventure that everybody's trying to be involved in, like to get to AGI. And that is, I guess, a political question, because eventually it's not clear. The current system doesn't actually help with that happening. Like, how can if it is going to cost $10 million to train your model, and you don't have $10 million, what can you do? Well, you can't do it. Basically, you have to find something else to do. And so, is there a way to make this more accessible? And obviously, it's not easy because money is money, and it's expensive. And part of it will be obviously, I think, cost going down, because cost going down has been one of the great stories of computer science. So that will make things more accessible over time. But then again, like people who are still really wealthy will be able to do things even at a higher order of magnitude. So there's still going to be some problem of this kind of balkanization of different tiers of research. And so I think it would be worth thinking about this collectively. Like what can we do to make sure that great ideas get to see the light of day in large systems, if that is really necessary to reach their full potential.
Yeah, yeah. Yeah, that's a good point that hopefully there's still um, kind of conceptual breakthroughs that still have to happen and then that don't require the scale, maybe to at least prototype them. And then the ones that do require scale, maybe there's some sort of sharing.
Yeah, yeah, yeah. And I do
Yeah,
think
yeah.
there's room for conceptual breakthroughs still. And I don't think that like we should be, or there should be like a pervasive feeling of hopelessness or something in the AI community that like
Hmm.
if nobody can do anything except like the very most wealthiest corporations. Like I don't think we're at that point. I think ideas still have weight and merit, and there's still plenty of good ideas to be had that can be shown on smaller scale. But for us to do that, we have to also allow ourselves not to always have to beat some arbitrary cutting edge benchmark. I mean, I've never liked benchmarks. The
Mm.
field loves benchmarks. But I mean, if it's getting to the point where winning on the benchmark costs millions of dollars, then the benchmark is no longer going to be helpful. And
Yeah.
so we need to be able to. It might be that there's some smaller benchmark you can use, but you shouldn't be required to always get the state of the art on like the current hot thing. In order for me to take notice of you, you may have a great idea, just you can't afford to do that. And so we
Hmm.
have to wrestle with that as well.
Yeah, and then one more thing that I wanted to just maybe quickly touch on, because like one nice thing about doing this podcast is kind of uncovering more interesting ideas that are hidden inside PhD theses. I thought this idea of it was called plastic neat
Yeah.
was really interesting as well, and I know that I think it's connected that later you worked on like this paper called back propamine, which are basically looking at different update rules for the synapses
Hmm.
in a neural network. And here in plastic neat, like all the way back in your thesis, this was looking at evolving the rules for like these Hebbian rules for the
Yeah.
synapses.
Yeah, that was because, I mean, I was like going back to NEAT in those days. I was really interested in evolving a brain, like a real brain-like thing.
Hmm.
And I guess I was very aware that brains are plastic or learn over their lifetime. And this sort of conventional neuroevolution system where you just evolve the weights of a network isn't like that. Like it's a static structure
Hmm.
that just does whatever it does. There's some subtlety there though, because recurrence, like if you have recurrent structures which can evolve, then in principle they can do things like learn, but the learning is happening
Hmm.
inside the cycling activation rather than in the weights.
Hmm.
And so it's kind of confusing and subtle, but nevertheless, it seems that that's probably not the most efficient way. Like the most efficient kind of learning probably is changes in weights. And so then you can see that does happen inside of biological brains, which have plasticity, and they have weight changing types of rules like Hebbian like rules in them, and they have others too.
Hmm.
And I mean, I was taking like graduate neuroscience in grad school, and so I was looking at graduate neuroscience and trying to think like, well, how could I put these kinds of rules into neural evolving systems? And so I kind of would have, like, I guess as a grad student, I would have liked to solve everything at once. So I was like, all right, we'll evolve increasingly complex brain-like things, and they'll be plastic, and like, I'll solve all of AI basically in the thesis, which I think a lot of grad students start out thinking, but just solve all of AI in one thesis. So I just had to squeeze that in there and like start taking, I guess, getting a little bit moving in that direction. Ultimately, not as far as I probably would have liked, but to get to
Hmm.
get to the idea that like, yeah, neat can, instead of just define the weights, it can define the rules, and the rules
Hmm.
of how weights should change, and then you've actually evolved a learning system or even a learning algorithm rather than just evolving a static structure. And it's really related to meta learning, which is obviously a topic today that's
Hmm.
popular. So it's like evolving the rules to allow a neural network to learn is just one type of meta learning system. It is the natural kind, of course, because evolution did evolve our brains, and our brains can learn. So we are part of a meta learning system. But I was trying to just basically create something like that. And I guess for some time it looked like this is one of the things that makes evolution distinct as an algorithm from, say, gradient descent, because like evolution can evolve things that are higher level than just weights, like rules. And so like maybe that's like one recommendation for evolution over something like gradient descent, because it's just going to optimize weights. But then eventually it's become clear that like, well, you can do meta learning with gradient descent. I mean, now we know in recent years that this is now popular, and so backpropamine, like which comes way later, is taking
Hmm.
advantage of this fact that, well, we'll just actually optimize the parameters of the learning rules themselves through backpropagation. And then like we can get something like this, like plastic neat, but without neat, sadly, perhaps. So now it's really just gradient descent, but it is like in the tradition of what I was interested for many years with this plasticity, but
Hmm.
through backpropagation. And we did that work with Thomas McConey was the lead author there at Uber, and it was cool to see that, yeah, you can actually optimize the learning rules through gradient descent.
Hmm. Yeah, yeah, and yeah, that's another area where it seems like this idea of it might be tough to initially get like state of the art or something with this, but if you're kind of solving the problem in a new way, then it might be promising to look into.
Absolutely, yeah. I mean, and that's right. It's something novel, and whether it gets, I mean, there's some obscure problems if you look at the backpropping paper where maybe it's state of the art, but they're not like mainstream benchmark type of problems. And so, yeah, if you look at it and say, well, what is this really good for? It's not beating ImageNet or something, and then dismiss it. That would be pretty naive, I think, to look at it that way.
Hmm.
And so we do need to be more open-minded to that. Like, oh, well, it's valuable because it's interesting and it's a new way to do things. And yeah, brains are plastic. Like it is okay sometimes to just say something's interesting for reasons other than that it's beating a benchmark. I think that's kind of a big thing our book is about. When our book is called "Why Greatness Cannot Be Planned," and the
Hmm.
subtitle is "The Myth of the Objective," and it's sort of saying that, like, look, sometimes you really only have the instinct for interestingness to go on. You don't have a metric always that will basically validate that this is a direction you should go. And so we are remiss, I think, as a field, if we always have to have an objective metric for every single thing that we allow through like the gatekeepers of what should be published and whatnot. And so, yeah, I think this is a good example of like this is a totally new direction. It's opening up new possibilities. Let's explore it because we're explorers, not because it's beating something, but because we need to explore.
Yeah, yeah. Yeah, so I guess if you had any, if you wanted to like throw in any pitches for like your new team at OpenAI and what you'll be working on, I also wanted to like close with some form of advice. And I thought maybe like looking back over what you've done so far, like one thing that sticks out is that you've really been able to take a long-term focus, I think, with some of these problems. Like for example, with NEAT, we talked about how it shows up still in Enhanced Poet. So do you have any, it's always hard to come up with like general principles, but yeah, do you have some things that come to mind of like how to keep this long-term focus on problems?
Let's see. For the first, just to say something quick about the team at OpenAI. It's true, I'm starting this team at OpenAI, which is focused on open-endedness, and I'm super thrilled to get to do that because it's obviously a topic that I love. And so to be able to start a team there is so exciting because they do have computational resources that
Mhm.
that really could support doing something like this, like, and seeing its full potential. And so we are hiring now. We're building up the team. It's going to be a small team. But at the moment, the job solicitations are still open. So in fact, people who hear this could feel free to apply, and I'd be happy to see those applications. And we're going to be looking at, I think, in broad strokes, just basically solving open-endedness, like the never-ending algorithm. Can it be created? Like that's a very high bar. It's like solving AI. But I
Mhm.
just, let's take a stab at like really being ambitious here. Not just a little thing like, well, let's just see if we can make this produce some cool stuff for a few days. let's see if we can run this for 15 years straight, and it just gets cooler and cooler and cooler. And I
Mm.
recognize this is extremely ambitious, but I would like to try to actually crack it and see how we can do that. So that's what our team's going to be doing, and it's obviously in support of AI because it's OpenAI, but it's because I strongly believe that the ability to do things open-endedly is essential to getting to AI and essential to being AI. Like that
Mm-hmm.
artificial intelligence or AGI will be open-ended. It will be creative, not just able to solve a problem or answer a question, but it'll be able to be creative because that's probably the most salient aspect of human nature. Like in my view, is our creativity. It's not that we're human calculators. Like I give you two 5-digit numbers and you add them up and we say, oh, the humanity of that. No, it's when you come up with a new amazing piece of music or a new story or a new invention. Like that's the humanity. And so if we're really going to have human level intelligence, then it's going to have an open-ended aspect to it. And so that's why I think that there's an open-endedness team at OpenAI. There's a lot of opens in that, a lot of use of the word open. Yeah, so that's that team. And
Mm-hmm.
so to address the last question of advice, let's see. So the question of how do you maintain like a long-term persistent vision, or can you, or maybe alternatively, can you see that what you're working on is something that will have relevance in the long term? Um, it's a super interesting question. It's like, how should you approach research as a young new researcher? That's so interesting.
Mm-hmm.
I like to think about this. And I do think that it's almost impossible to you should not index on will something be relevant 20 years from now. It's just basically impossible is the problem. The fact that we may still use NEAT for something 20 years after I thought of it is just a coincidence that I would have no control over and didn't necessarily, yes, suspect at all. And so I don't think that's a good heuristic for deciding what to do. It's a little bit one of the problems with it is it's sort of an objective heuristic, and I'm a very non-objective type of person. So I think and look at our book. Like I think we shouldn't be too objectively driven. If you want to be creative and you want to do something radical, I think you shouldn't be too much focused on like what will this accomplish. So it's the same with things like will it be relevant? Will it have a lot of citations? Will you make a lot of money? Like I think these are all really bad ways to move into radical directions. Like radical directions you move into because they're super interesting and only because of that, I think. And so I think it's more about, in some way, fearlessness, like not being swayed by what is currently dogmatic in the field, not just believing the current dogma, and being willing to just go in a very independent, radical direction because you believe in it. But you have to believe in it. So you don't go in directions just because they're radical. That would be dumb too. You have to really believe it's a good idea. Obviously, there's lots of radical directions that are terrible and will lead you flat into a brick wall. But if you really believe in something and it's going in another direction, I think then you're on something that could be interesting. There's basically two strategies I think in research. You can jump on the bandwagon or you can jump off the bandwagon. And they both have pros and cons. And the vast majority, though, will jump on the bandwagon. And the bandwagon right now is deep learning. And so the vast majority will see that indeed it's very successful and try to piggyback on top of that and think of something new that increments on top of deep learning. And then there'll be a small fraction who jump off the bandwagon, buck the trend, and not necessarily reject it. Like they're not saying deep learning is wrong, but they're just saying let's try a different direction. Maybe it's complementary ultimately, but just something different. And then you have advantages in both. Like if you go on the bandwagon, the advantage is it's pretty safe. Like you're probably doing something that's like likely to at least work a little bit, and there's already a built-in community that cares. If you're off the bandwagon, then it's not that safe because like nobody cares. But you have this other advantage, which is that you no longer are like one out of a million trying to get attention. So you're on your own and you can be noticed. And if it does turn out that you're moving in a good direction, you'll be the leader of that whole area, and get all the credit go to you. And so that can be really valuable if it works out. And I think both approaches are legitimate, but it's better to get off the bandwagon if you can. It's just much more dangerous and risky, because the payoff is going to be higher because the bandwagon is already full. But it's easier said than done. So don't go off the bandwagon just because it sounds cool. You've got to really have a good reason to get off of it. But that's the way I would think of it. I would say I would guess that if you get off the bandwagon in a successful way, people probably will be talking about it in 20 years, because it's so unique and different, and you've taken the world in a new direction. And you'll feel that, when you do it. It's kind of probably ahead of its time because people aren't thinking about that yet. But trust your instincts. That's the thing. Like, you might not have evidence to prove that this thing is the right thing to do, but you got to follow your instincts.
Right. Yeah. Yeah. So trust your instincts, be fearless, and find problems that you really believe in.
Yeah, that's probably a good way to sum it up. Yeah, and don't worry so much about an objective. Yeah, I guess I was almost gonna say read the book, but I don't like to pitch a book. Yeah. So just the themes in our book basically support this kind of argument. Like, I've argued a lot about this, like how to actually do something innovative and like what the right approach is. So if you wanted like more argumentation, like what actually is behind this kind of argument, that's where we've like really worked hard to figure out like what is the real like formal basis for believing that you should approach life or something innovative like research in that way.
Yeah, I see. Well, I'll put the link to the book in the show notes, so listeners will have a nice follow up to read. And
Okay.
otherwise, yeah, this has been really great conversation. Like going back, looking at what you did in the thesis, how it connects to what you're doing today, and then also just some good advice and some good philosophy, I think.
Yeah, thanks. This has been great. It's great to have a chance to reminisce about something from a long time ago, and I think it's a great idea for a show too. Really interesting to hear what people were thinking like when they came out with their ideas. It's great. I'm looking forward to listening to others.